This will be first of two lectures on basic graph algorithms. As before, my slides are modifications of those provided by Kevin Wayne, associated with the textbook. In this section, we'll review some basic graph definitions and look at two applications, connectivity and testing by part tightness. And in the following lecture, we'll examine connectivity in directed graphs and topological ordering of directed acyclic graphs. Okay, so a quick review of terminology for undirected graphs. A graph, of course, is a pair, usually called V and E, of nodes or vertices and of edges, which are pairs of nodes. In the case of undirected graph, those are unordered pairs. And we use them to capture pairwise relationships between objects, the nodes being objects and edges representing some kind of relationship between them. We typically have two size parameters, the number of vertices, which we should call n, and the number of edges, often denoted m. Okay, so here's a drawing. We usually draw graphs because they're not very nice to read, of the graph that has a vertex set 1 through 8, and this collection of edges, although notation's a bit funny. We usually write these edges as pairs like this. Okay, for this graph, we have 11 edges on 8 nodes. Okay, lots of applications, but just very quickly mentioning in a few. In communications, you might have phones and links between phones, or computers and links between computers. In an electronic circuit, you might have nodes or gates, and an edge represents a wire between two gates. Okay, various transportation problems are very natural. For example, airports are nodes, and edges represent flights between airports. Okay, and various kinds of social relationships. You might have people, say, actors as nodes, and an edge between two nodes if those actors appear together in a movie. And lots and lots of other things. When we describe graph algorithms, we don't really need to worry about how the graph is represented in a data structure, or at all for that matter. But when we want to do complexity analyses, especially in the case of polytime algorithms, the data structure representing the graph matters. There are two very widely used representations. One is the adjacency matrix. Okay, so when we have a n by n Boolean matrix, or 0-1 matrix, where the cell at location uv has a 1 or a true if uv is an edge, and 0 or false if there's no edge uv. In this representation, so a few properties. First, there's two representations of each edge. Right? Consider this edge between 2 and 4. It's represented as 2 and 4 being a 1, and also as 4 and 2 being a 1. Okay, so strictly speaking, to represent this, you'd only need the upper diagonal or the lower diagonal of the matrix, but we don't have nice computer implementations of those objects. So we have n squared, size n squared space, regardless of the number of edges, right? We have n vertices, so n squared locations in the array. So our size is big O of n squared, and it's also big omega of n squared because the array really takes time, or space proportional to n squared. So theta of n squared, space, to store the graph. Okay, and that's the case whether it has 0 edges or n squared edges. Okay, checking if a particular vertex is in the graph is just one lookup in the array. So that's theta of 1 time, so that's fast. But identifying all edges, or maybe it's more enumerating edges is a term we use more often. Right, if we want to list all the edges, or if we want to do a search that involves visiting all the edges, that requires times theta of n squared, because we don't have a way to just look at edges. We have to look up all pairs of vertices to access all edges. All right, the second one is the adjacency list representation, where we have an array of lists. The array is indexed by nodes, right? And the list associated with each node is a linked list, normally of the other nodes that are neighbors, right? So, for example, here in this picture, this is our array of nodes, indexed by nodes, and associated with 5 is this linked list containing 2, 3, 4, and 6, indicating that in the graph the neighbors of 5 are 2, 3, 4, and 6. Okay. So again, 2 representations of each edge, right? Because the edge 2, 4, for example, appears as a 2 in the list for 4, and as a 4 in the list for 2. Okay, space theta of m plus n, which we'll come back to in a minute. Checking if UV is an edge takes time on the order of the degree of U, right? So the degree of vertex is its number of neighbors, right? To check if UV is an edge, we would go to the list for U and scan that list to see if V appears, right? So the amount of time we take is proportional to the length of the list of neighbors of U. Okay. Enumerating all edges requires how much time? Time to run down all the lists, okay, which we claim is theta of n plus n, same as the space. And why is it that? Well, for the array, we need theta of n space, some constant times the number of vertices, right? And then for the lists, we need the sum of the length of all the lists. And what is that? That's the sum over all vertices of the degree of the vertex, right? The number of neighbors it has. Okay, since every edge appears twice, right? In 2 of those lists, one for U and one for V, that sum is 2m, twice the number of edges, and then we have some constant, of course, for the amount of space for each node and the linked lists. So that gives us a total of theta of n for the array, theta of m for the linked lists, for a total of theta of m plus n size. Okay, lots of problems in graphs involve paths and connectivity. So a path in an undirected graph is a sequence of nodes, okay, with the property that each consecutive pair is joined by an edge. Right? So for example, we have a path 2, 5, 3, 8. That's the sequence of nodes. Okay, and we have an edge from 2 to 5, 5 to 3, and 3 to 8 in the graph. path is simple if all of its nodes are distinct. Right? So path that's not simple revisits one of its nodes. Okay, so I can just quickly draw such a path. So if I take this path, there, okay, that path is not simple because it visits the two twice. All right, and underwrite the graph is connected if every pair of nodes has a path between them. In other words, from any node, you can get to any other node in the graph. It's called connected. So if I to view this drawing as two different graphs, this graph would be connected, and this graph would be not connected. Cycle is a path in which the first and last vertices are the same. Okay, and there's at least two vertices. Okay, so here's an example of the cycle C. It's the sequence of nodes 1, 2, 4, 5, 3, 1. That's here 1. Oops. 1, 2, 4, 5, 3, 1. And a cycle is simple if all the nodes are distinct, except of course the first and last, which I just mentioned twice, but don't appear twice in the structure. An undirected graph is a tree if it has two properties. It's connected and it has no cycle. Here's an example of a tree. This graph is obviously connected, obviously has no cycle. Lots of useful things about trees. Properties stated here. If G is an undirected graph on n nodes, then from any two of the following statements, you can derive the third and obtain the third. They are G is connected, G is not containing a cycle, and G has n minus 1 edges. So let's look just briefly at this. The first two are just the definition of being a tree, right? Connected and having no cycle. So this claim that properties 1 and 2 imply 3 is the property of trees that we usually state as the following: a tree on n nodes has n minus 1 edges. Right? And the other two are just variations on this. So if you look at a tree, it has this simple structural property that's kind of captured by this theorem, but intuitively it's captured by this argument. Suppose I have a tree on n nodes. I can count that it has n minus 1 edges. And suppose I want to have one more node. So let's just add here a 10th node. And now I want to have a tree. So it needs to be connected. So in order to be connected, I have to add another edge, right? And so I'll have one more node and one more edge. And obviously, if I added two more edges, I would have a cycle. So that's not going to do it. Okay. And these three versions of what's in this theorem, right, all capture this in various ways. So, for example, the claim that 1 and 3 imply 2 is the claim that G is connected and it has n minus 1 edges. It doesn't have a cycle. Why is that? Because if it's connected and has n minus 1 edges, it doesn't have enough edges to make a cycle. Right? And you reach that by essentially, this same kind of argument, similarly for the third. Okay, sometimes we like to designate one vertex of the tree as special. And we typically call that the root. Okay, so here's a tree. And I'm just going to copy of it. Okay, and I'm just going to pick this node and call it the root. And now I have a rooted tree. Okay, but in most applications where we find use with have a rooted tree, we like to think of the edges as being oriented either towards or away from the root. Okay? And to kind of capture that in an intuitive way, not make that too big. Okay. We typically draw it like this. Okay, with the root at the top, and then neighbors of the root just below it, right? And any additional neighbors that are farther from the root below those, etc. And then we talk about this kind of represents a hierarchical structure. And we have terminology related to that. So, for example, the node closer to the one closer to the root than a node V is the parent of V. And if you have a node that's one farther from the root, that is a child of V, etc. Okay. We're interested in many kinds of problems related to connectivity. Obviously, for example, I can't travel by air from one place to another if there's no flight, and that's a connectivity question, right? Link to the internet is broken. All right, so simplest one is ST connectivity. Given a graph, there's two nodes in the graph, call them SMT for starting terminals. That's the question: is there a path between SMT? It's natural optimization version, right? The shortest path problem. Given a graph and two nodes SMT, what is the shortest path between SMT? Okay. Of application. For example, fewest hops in the communication network, fewest stops in a flight, etc. Okay, so we'd like an algorithm to find shortest paths, for example. And one such algorithm is the breadth first search, which is one of a number of graph traversal algorithms. So the intuition behind this algorithm is we start from some vertex S, and we kind of explore outward from S in all possible directions, adding nodes in layers according to how far they are from S. Okay, so we start like this. Let layer 0 just contain our start node S. Okay, and then we construct layer 1 by taking all neighbors of S. Okay, that's all neighbors of S. Okay, and then for layer 2, take what? We take all nodes that are neighbors of a node in L1, but excluding the ones that are already in S of L1. Okay, and those form layer 2, and those are nodes that are with they're at length a distance 2 from S, the shortest path from S to 2 is 2, 1, 2. In general, layer I plus 1 is obtained by taking all nodes at layer I, taking all their neighbors, and leaving out the neighbors that have already appeared at some earlier level of I plus 1. So it's not too hard to see the following, that the nodes in layer I consist exactly of the nodes at distance I from S, and that there's path from S to T if and only if T appears in some layer. Right? So if we have a graph S is here and T is here, then when you follow this process from S, you'll get all of the nodes in here, but you won't get the T, obviously. When we do a breadth-first search, we can think of building a thing called a breadth-first search tree corresponding to that particular search. So I'm doing an illustration of an algorithm and building the tree at the same time. So here's our graph. And we'll start with vertex 1 at level 0. Okay. And then level 1 will have all the neighbors of vertex 1. So what are those? 2 and 3. And then layer 2 will be what? Well, all the neighbors of vertices 2 and 3, except for 1. Right? So we just look vertices that you can, right, that are one edge further from the root than 2 and 3 are. Okay, and that gets us all these. And finally, level 3 will be just the 6. Okay. Now, if we include in a diagram, as we've done, but haven't mentioned the edges that we use in adding neighbors to the next layer, we get a tree. So that's a breadth-first search tree. And of course, there are some edges that we don't use. Right? Okay. So property, T is a breadth-first search tree of G. Okay. And XY is an edge of G. And the levels of X and Y differ by at most 1 in the tree. Okay, why is that? Well, consider this node 5. Okay. Where can a neighbor of 5 be in the tree? Okay. Well, any neighbor of 5 has only 2 options, well, 3 options, right? One is it could be in the same level, right? Or it could be in the previous level, the 5, or it could be in the next level. Okay, that's the only possibilities. Why? Well, why can't 5, let me just say, why can't 7 have 1 as a neighbor? Because if 1 and 7 had an edge between them, we would have put 7 on layer 2, on layer 1, right? And similarly, why is there no edge between 3 and 6? Because if there was an edge between 3 and 6, 6 would have had to be at level 2. Okay, here's a sketch of the implementation. And the input is the graph and the special vertex set. Okay, for each vertex, we mark it not explored. We mark all the vertices not explored, except that we mark S, the start vertex, as being explored. And we set L0, the set of vertices at level 0, to be just S. Okay. And what do we do? So this is building tree layer 0. Build the other layers. That's why we inductively we're going to construct a layer I plus 1 from layer I. Right? And we're done when we're at a layer that doesn't have any vertices in it. So that's while the current layer doesn't, right, has some vertices, we have to check with our neighbors to make the next layer. Okay. So how do we do that? We set layer I plus 1 to be the empty set. And then for each vertex in layer I, we go through all its edges. Right? Okay. So we look at all its neighbors. And for each of its neighbors that's not explored yet, those are the ones that haven't appeared in an earlier level. Right? We mark them explored, and we add them to layer I plus 1. That's it. Okay, so how much work does it take? Well, claim it takes time big O of n plus n, and that would be linear in the size of the data structure we're using, assuming an adjacency list representation. Okay, that's already of size theta of n plus n. We're going to have to inspect maybe all the edges. Okay, so we're certainly going to take time, at least n plus n, but maybe it takes more time. If you're not too careful, if you're not careful enough, that's what I seem to get. Let's consider these two for loops. Let's call this the outer for loop and the inner for loop. We can argue each node occurs in at most one list. Okay, the body of that for loop is essentially taking nodes off that list to explore, right? Okay, so the total number of times the body of that outer for loop executes is at most n, once for each node. So that's n. And then if you consider the inner loop, okay, for each node view, we have to look at all of its edges, right, to see which ones are explored yet and have to be in level I plus 1. There's a most n of those. So n of those, so this together is clearly an upper bound of n squared. The algorithm actually runs in better time than n squared. It runs in big O of n plus n. And in fact, big theta of n plus n because we have to inspect this data structure that's of size 1 plus n. Why? When you consider a node U, okay, there are degree view and edges. So the total amount of work is just the sum over all the nodes of the degree of the node, right? We've already seen what that is. The sum over all the nodes of the degree of the node is 2n, and that's the total amount of work that we do in this algorithm. Okay, so now we want to talk about connected components. So a connected component in a graph, an undirected graph, is a subgraph that consists of a set of vertices, okay, all of which are reachable from each other, all of which are connected to each other, right, and a maximum subset. Right? Okay, so for example, here, this is a connected component, and this is a connected component, and this is a connected component, right? Within each of these blobs, every two vertices have a path between them, okay? And there's no vertices that have a path to those that are not included. So the connected component containing S for some vertexes is a subgraph induced by the following set. Okay, the set V, which is reachable from S, or which has a path from S. So what does the induced by mean? It means you take a set of vertices and you include all of the edges on those vertices. So the connected component containing S is constructed as follows. And let's use this as an example. Connected component containing 1 is you start the 1, right? Include every vertex that you get to from 1 by a path. and you include all the images. So more properly, this is vertices of the connected component containing node 1 are these. Okay, so if we want to construct connected components, it's a very simple abstract algorithm that works. So suppose we want to build R, our set of the set of vertices in the connected component containing S. Okay, what will R consist of? And it'll be all the nodes with a path to S. Okay, you can build it as follows. First, include just S. Okay, and then as long as there's an edge, UV, where U is in the set and V is not, we can add V. What does that mean? Well, suppose we're working our way along. Here's my set R. Okay, and it includes only vertices reachable right from S. Only vertices where there's a path from S to that vertex. And suppose there's an edge to another vertex, and that vertex is not in R. Well, clearly, if I can get to U from S, and then I can get from U to U by an edge, I can get from S to U. So I can add set R. So this algorithm is non-deterministic. There may be many choices of which vertex to add at some points, and I haven't said how to choose one. But however you choose, right, when you get to the end, you have again a set of vertices of the connected component containing S. And two particular strategies for how you choose that edge correspond to breadth first search and depth first search of the component. Okay. In the case of breadth first search, we explore and construct the set distance of vertices from our start vertex. So now the application to bipartite graphs. An undirected graph is bipartite if the nodes can be colored with two colors. Here they're called blue and white, but it doesn't matter what we call them, such that every edge has one white and one blue end. No edge has both ends the same color. Or equivalently, the vertices can be partitioned into two sets. So every edge is between two sets, and no edge falls with both ends in one set. Lots of applications. So stable matching obviously is about bipartite graphs, right? Where students could be blue or hospitals, for example. Lots of kind of scheduling problems, assignment problems of various sorts, where you have two different kinds of objects and you need to kind of match them up somehow. Right? So here's an example of a bipartite graph. White vertices, blue vertices, all edges are from a white, between the white vertex and the blue vertex, and there's no edge that has both ends that are set. Okay, we might have reasons to check to what the test of a graph is bipartite. For one reason is lots of problems become much easier on bipartite graphs than on general graphs. You might have some structural property you're interested in, whether that in an application that corresponds to the graph be bipartite or not. Okay, to build an algorithm, we need some kind of property to exploit, right? You need to understand the structure somehow. And to illustrate this, here's a bipartite graph. This is obviously bipartite. This is a drawing of the very same graph. but it's not too obvious whether it's bipartite. Right? And so if we had a very large graph, it might take some effort to figure out whether it's bipartite or not. And the question is, what kind of algorithm can we use for that, and do we have a very efficient algorithm for that? So we talk about obstructions to properties, meaning some kind of substructure which guarantees some general property does not hold. In this case, if a graph is bipartite, it cannot contain an odd length cycle. So graphs with odd length cycles are not bipartite. And how do we know that? Well, it's not possible to properly two-color an odd length cycle. Right? Therefore, if the graph contains an odd length cycle, we won't be able to properly two-color. So here, for example, this is properly two-colorable, right? We have every node is colored white or yellow, but the edge has the same color on both ends. What if we have an odd cycle, as in this case? Well, let's try to color it. So let's just pick a vertex and color this one red. Then the neighbors, and there's exactly two neighbors because it's a cycle, right? The two neighbors have to be blue. And what about their neighbors? Well, each of their neighbors also has to be red. Okay, and what do we find? Well, we have an edge with two red ends. Okay, so this is not a proof, but it generalizes pretty easily. Just imagine any odd cycle, and you can just execute this process, right? Color one vertex, then color its neighbors the opposite color, color their next neighbors the opposite color, right? And continue. And because there's an odd number of edges, you necessarily reach this state where you have a monochromatic edge and the same color on both. So, claim if G is a connected graph, and you do a breadth first search, starting from some node S, it doesn't matter what node we start from, okay? And you get layers, L0 through LK. So then exactly one of the following holds. So if we just look at the first part of each condition, it's obvious exactly one holds. Either no edge of G joins two nodes of the same layer in the tree, or some edge in G joins two nodes of the same layer. It's obviously exactly one of those. The interesting bit is the second part. Okay. If there are two nodes, if there's an edge between two nodes of the same layer, if there's no edge between two nodes of the same layer, G is bipartite. And if there is an edge joining two nodes of the same layer, then G contains an odd cycle, an odd length cycle, and therefore is not bipartite. Okay. Intuitively, this seems reasonable, right? Suppose this is a breadth first search tree with layers. Okay. So we can color as follows. Let me color red layer 1, blue, 2, red, 3. Now, it looks like we don't have edges with the same color on both ends. Right? But we have to actually prove that still. Okay, but for the edges in this picture, right, the two ends have different colors. Okay, if we go to this picture, though, suppose we do have an edge joining two nodes at the same level. Well, look what happens if we follow this path back to the start and then follow this path down to this node. What do we see? This path with the same length. Okay, so you take those two and you have a path of even length, and then you add this node, this edge that joins the two nodes on level 3, and you have a cycle of odd length. Okay, so obviously in this case, graph is not bipartite. Okay, so this leads us to a proposal for an algorithm. Okay, given a graph G, and we'll assume for now that G is connected. Run breadth first search on G. We can start from anywhere we want to. Okay, suppose the BFS levels are L0, L1, L2, etc. Then we're going to color the nodes for every node V. We'll color it red if it's in an even level. And we'll color it blue if it's in an odd level. Okay, and then we run through the edges and we see if there's an edge that's monochromatic, an edge that has the same color on both ends. And if there is such an edge, we output that it's not bipartite. And if there's no such edge, we output that it is bipartite. What if G is not connected? Well, we just test each of the connected components. We can use breadth first search to find the connected components. And then the entire graph will be bipartite if and only if each of the components is bipartite. For runtime, what do? Well, we have to run breadth first search times theta of n plus n. We have to cover the nodes. We can do that at time theta of n. And we have to check the edges to see if there's a monochromatic edge, and that takes time theta of n, right? The total time is just the sum of those. N plus n, right, which gives us theta of n plus n. Okay, which is again the size of the data structure representing G. So very efficient. Okay, what about correctness of this algorithm? For correctness, what would we want to do? Suggest three things. It always terminates. Okay? And when it terminates, it outputs either bipartite or not bipartite. And then if G is bipartite, it outputs that it is. And if G is non-bipartite, it outputs that it's not. Okay. So for one, that's easy because we have three stages in the algorithm. Each takes time. They go of n plus n and stops. Right? And at the end, it outputs either bipartite or not bipartite based on a simple condition. What about 2 and 3? Well, it's easier to prove slightly different statements. It's sufficient to prove these because the algorithm always terminates and has only two possible outputs. So we can change the condition. If you take conditions in 2 and 3 and take their contrapositives and then apply an obvious replacement of negation, you'll get these two, okay, which is that if it outputs bipartite, G is bipartite, and if it outputs it's not bipartite, G is not bipartite. Okay, so we want to show that. Okay, so let's go back to this lemma and prove it. Okay, so the first one is, okay, we need to show if no edge of G joins two nodes at the same level, G is bipartite. Okay, so let's suppose there's no edge joining two nodes at the same level. Okay. So that eliminates edges like this or like this, right? doesn't eliminate monochrome edges like this. Well, we already know that those edges cannot exist, right? Because we proved that each edge joins two nodes, that no edge joins two nodes that are more than two levels apart. Since we've excluded nodes as joining nodes between in the same layer, we know every edge joins two nodes in adjacent levels. Okay. Levels and layers is synonymous in these slides. Okay, so we color, as we described before, right? Even layers blue, odd layers white. And we know that edges only appear between adjacent layers, and therefore all edges have different colors on their two layers. And in this case, it's easy to see that the algorithm correctly opens bipartite. In the other case, right, we want to show if there's two nodes in the same layer with an edge between them, G contains an odd-length cycle, and so it's not bipartite. Okay. Suppose there's such an edge, right? Let's say this one. Okay. Then find the lowest common ancestor in the BFS tree. Start from X and Y and head back towards the root until you find a common ancestor. Okay. That's some name for I. Now let's consider this cycle that goes from Z to Y, and change from Z to Y to X and back to Z. What's the length of that cycle? Well, it's this distance plus this distance, 2I, and not minus J. Okay. Plus this. So twice this is an even number, add this one, it's an odd number. So you have an odd length cycle. Okay. In this case, the algorithm correctly equals not bipartite. Corollary is G is bipartite if and only if it contains no odd length cycle. Okay. That is, the odd length cycle is the only obstruction to bipartiteness in a